out of chapter 14 there. And so I guess we're going forward, I guess, since we're just in 13. All right. So we pretty much have spoken about or lectured on all the different sort of organic groups. Really, there's just kind of two left that we're going to talk about just to kind of complete it. And these are really nitrogen containing groups. So these guys basically have functional groups that have nitrogen as really the main part of their functional groups. And amines basically have the functional group of like NH2, which is really a derivative of NH3. So if you remember, NH3 looks something like this. And basically amines are sometimes referred to as ammonia derivatives. They essentially have one less sort of hydrogen involved in there. So if we look at these guys, we have a nitrogen attached in the way here, and we have sort of our nitrogen that can have basically two hydrogens, one hydrogen or no hydrogens. So that's a nitrogen containing group with actually no hydrogens. This is a nitrogen containing group that has two hydrogens involved. So you can have, kind of multiple hydrogens, usually two. And then if you add more carbons to this nitrogen, so for example, if we had another carbon attached, we lose a hydrogen. And if we had one more carbon attached, like we do on the very bottom guy there on the left, we end up with no hydrogens attached. But this nitrogen sort of containing group is really based off of ammonia. It has similar sort of properties to ammonia. And that is basically the functional group here of an amine. Now, much like carbons, much like alcohols that we've seen, we could actually classify amines in the same way as we do those guys as primary, secondary, or tertiary sort of amines. And it kind of works the same way. And basically, it is the nitrogen that's important. And when we look at the nitrogen, it is attached directly to one carbon. One carbon then means that this is a primary amine. We look at the nitrogen here, it is attached to one carbon, two carbons directly. That will give us a secondary amine. And if we look at this nitrogen here, it is attached to one carbon, two carbons, and three carbons. So that is our tertiary amine. So much like how we classify carbons as to how many other carbons are attached to it, just like we classify alcohols as to how many carbons are attached to the carbon that has the OH group here. When we're classifying our amines, we're looking at the nitrogen and we're looking at how many carbons are directly attached to the nitrogen for primary, secondary, tertiary. So just like the number implies, the easiest way to remember primary, one carbon, two carbons, and three carbons for tertiary. Any questions on that there? And again, here we see ammonia, which is really what they're all based off of. And here is our primary, one carbon attached, secondary, and our tertiary happening here. And you might even get an idea as to how we could go about naming these guys. There is a one carbon group attached to our amine. One carbon group is methyl, and we could just put amine at the end of it. So that would be methylamine. This guy has one methyl group there, two methyl groups there. That is two methyl groups, which is the dimethyl, and we could call it amine. Lastly, here we got this guy, which has one methyl group, two methyl groups, and three methyl groups. That is trimethyl. And again, we could just put amine at the end of it. So that is, one way that you can sort of name these amines kind of like what we did with ethers, kind of instead of going to the oxygen and the groups attached on either side of the oxygen, you go to the nitrogen and find the groups that are attached, obviously in alphabetical order, like we've done before. So simple amines are named as alkyl amines, which basically just means you take the group and you put amine at the end of it. We list the names of the alkyl groups that are bonded to the nitrogen atom in alphabetical order, and then obviously put amine at the end of it. Again, here, if we look at this, that is basically a ethyl group attached. So ethylamine. This is a primary amine. Again, 2 hydrogens, 1 carbon attached. This again is the one we saw on, I think, on the other slide there. That is 2 methyl groups. So our dimethyl amine. This again is a secondary. And this is 3 different groups here. That is an ethyl group. And that is a methyl and a methyl group. So that is, if I can get over there to write. There you go. That is dimethyl. And we have ethyl. Like normal, we're going to go alphabetical order regardless of prefix. So E before M. So ethyl dimethyl amine. So kind of like what we've done in previously, we ignore the prefix and go alphabetical on it. Any questions on that there? So write the common name for each of these amines and classify them as primary, secondary, or tertiary. So take a moment here and see what you come up with. First off, let's classify it. So that's the nitrogen. And directly attached to the nitrogen, it's just 1 carbon, which means this should be a primary. We could do sort of the common name of it, which is find the group that's there. And in this case, this is a 3 carbon group, which would be a propyl group. And then since this is an amine, we would just write amine. So that would be propyl amine. Any questions on that name there? Looking at the next one here, we want to look at the nitrogen for our classification. We see 1 carbon attached to it, 2 carbons attached to it, and 3 carbons attached to it. So that is a tertiary amine. It also has no hydrogens there. We see our 2 methyl groups, which gives us our dimethyl. And then obviously here is our ethyl group, kind of like the one we had before. We can go ethyl first, dimethyl, and amine. So this is more of a common way of naming it. The IUPAC way of naming it is you'll sometimes see N's listed in the name, like N dimethyl ethane amine. And what this means is the groups here attached are attached to nitrogens, not carbons. So normally when they're attached to carbons, we use numbers. But here we use N to represent that they're attached to the nitrogen, dimethyl, or there are 2 methyl groups that are attached. And our longest carbon chain attached to nitrogen is 2 carbons, which is based off of ethane, and you put the amine on it. So this would be more of IUPAC way of naming it. We will go with common name here. Will work for us. But again, in case you ever see like NN or N something, that basically means, again, the group is attached to the nitrogen. For secondary and tertiary amines, they commonly will use that in place of a number. So numbers are reserved really for carbons. So here, because the groups are attached to nitrogen, they kind of do that. Any questions on that? So let's talk a little bit about aromatic amines. And as I was just saying, even with aromatic amines, sometimes we will use that N to indicate that the group is attached to the nitrogen here. And the amine of benzene is aniline. So if you remember, I think we saw this when we were talking about benzene. This is basically a benzene ring with an amine group on it. Again, that sort of historical name known as aniline, that sometimes will be really the base of the name. So if we kind of look at this guy here, that part is the aniline part, because that's sort of our functional group. That would be carbon 1 there, 2, 3, and 4. It really doesn't matter which way you go. It's going to be 4 no matter what. That gives us our 4-bromol aniline. In this case, we have, again, the aniline here. Now, unlike the guy over here, where the bromine is hanging off of a carbon, so that's a carbon right there. In this case, remember, a line with nothing there is a methyl, right? This methyl is attached to the nitrogen. So as I mentioned a second ago, that is where the N comes in. And that means N-methyl, which means the methyl group is attached to the nitrogen. And aniline would be obviously the rest of it there. Question on that. So again, that's what the N represents here, that the group is attached to the nitrogen. You typically will see that used, as I mentioned a second ago, with secondary and tertiary amines. You'll sometimes see that N sort of incorporated into the name, again, given the location where the groups are attached to the nitrogen rather than a carbon. Question on that there. So if we look at our nitrogen, again, it has 1, 2, 3 carbons attached to it, which means this is a tertiary amine. And we're going to do the common name. We're just going to look for the group. So really our nitrogen is sort of our starting point. So to the right of nitrogen, I see a ethyl group. To the left of nitrogen, I also see another ethyl group. Above nitrogen, I see a methyl group. So we want to go alphabetical, which means ethyl comes first. There's 2 of them, so that's going to be a diethyl, then a methyl, and then an amine at the end. Any questions on that name there? Over here, we look at the nitrogen. It has a carbon attached directly to it. And you don't want to miss this guy down here, which is also a carbon. So that's actually 2 carbons attached to it, which means it's a secondary amine. It's a secondary amine with a benzene ring, which means this right about here is that historical name of aniline. But we see hanging off of it is this group right here, which is an ethyl group. That ethyl group is not attached to a carbon, but it is attached to the nitrogen. So here's a good place where we could go with N-ethyl. Again, the N meaning that the ethyl group is attached to the nitrogen, not obviously a carbon, and aniline being the rest of it. Question on that name there. We also could obviously draw our line structures of these guys. Here's our primary amine. And again, if we just kind of count the carbons, that's 1 carbon, 2 carbons, 3 carbons, which is where the propyl comes from, an amine. And it is 1 carbon directly attached to it, which is why it's a primary. This is 1 carbon, 2 carbons, which is a ethyl group. This is 1 carbon, 2 carbons, 3 carbons, which is a propyl group, and alphabetical ethyl propyl amine. This being 1 carbon attached to the nitrogen, 2 carbons attached to the nitrogen, gives us our secondary amine. And lastly, this is 1 carbon, 2 carbons, which is our ethyl. Also 1 carbon, 2 carbons, which is our ethyl. And this is just 1 carbon, which is our methyl. Hence the diethyl methylamine. Again, here 1 carbon attached to nitrogen, 2 and 3 carbons attached, which makes it our tertiary amine. Now, because really the amines are based off of sort of derivatives of ammonia, ammonia does have the ability to hydrogen bond. If you remember, ammonia again looks like this. It is a polar molecule that has a bond between hydrogen and nitrogen. And that is what you need to hydrogen bond, right? To bond between hydrogen. Bonding is done between a bond between hydrogen and nitrogen, oxygen, or fluorine. So this has the ability to do that. In this case, the nitrogen being more negative, the hydrogen being more positive. So when you take an amine that has something like this guy being more negative, this guy being more positive, it's able to actually hydrogen bond with something like water, where the oxygen is more negative, the hydrogen is more positive, and it can interact with each other through hydrogen bonding. So that makes primary and secondary amines with, again, less than like 6 carbons, being relatively soluble in water because they're able to hydrogen bond with one another and mix really well. Tertiary amines cannot really hydrogen bond. So why is that? Again, if we just look at the structure of a tertiary amine versus a primary or secondary, so our primary amine is basically this. It's got 2 hydrogens. Our secondary amine is this. Since I'm not going to write the right thing here, hydrogen. There we go. It's got 1 hydrogen, and our tertiary amine has no hydrogens. So because there's no hydrogen there attached to the nitrogen, it cannot participate in hydrogen bonding. So obviously it would not be very soluble with water because it doesn't have that ability to interact well with water. Any questions on that there? So in terms of sort of solubility of amines, primary will be a little bit more soluble than a secondary because it can form more hydrogen bonds with water because it has 2 hydrogens. Secondary, obviously, more than a tertiary, and tertiary, obviously, no good in terms of hydrogen bonding, so it won't be able to do that. So like alcohols, the smaller the amines, including tertiary ones, are soluble because they can form hydrogen bonds with water. But once you get them into being really large molecules, the solubility really does start to decrease, kind of like what we see with a lot of organic guys. If you kind of build out the kind of nonpolar part of the molecule with a lot of really big part, it does definitely decrease the solubility. So if an amine has more than 6 carbon atoms, the effect of hydrogen bonding is diminished. The nonpolar part sort of gets in the way. It's sometimes referred to as steric hindrance. Like if you look at this guy, you know, you pretty much got nonpolarness there, nonpolarness there, nonpolarness there. You know, it makes it really hard for like a water molecule to kind of get in there and try to do some work. It kind of gets in the way, and it definitely decreases the solubility a lot because of all this kind of nonpolar regions that are there. Any questions on that there? All right, with that being said, take a look at each of these amines and decide, do you think these guys are these organic guys? I guess not necessarily all amines. Take a look at these guys and determine whether or not you think they should be soluble in water or not. All right, let's take a look here. So looking at the first one, it is an amine. It is a primary amine. Again, 1 carbon atom attached. That's not so big, so we would probably predict that this guy should be soluble in this particular case. Looking at this guy, this is a secondary amine, as is 1 carbon, 2 carbons, so primary there, secondary there. Again, not very large on both sides, so should be soluble. Water should be able to get in there and kind of do some hydrogen bonding with it. And lastly here, no nitrogen. This is basically an alkane. And that is nonpolar, which definitely will be using dispersion forces while our water is trying to use hydrogen bonding. So that guy should definitely be insoluble in water. Any questions on any of those there? All right, so amines again, obviously can do some hydrogen bonding. They actually can react primary and secondaries as like an acid and a base. So they can do that Bronsted-Lowry definition. So here's ammonia, again, is going to accept the H plus over. And the same sort of reaction occurs here with our amine. So the amine here will act as a base. The water will donate the H plus over. And just like it did here, it gains a hydrogen and a plus, gains a hydrogen and a plus, and makes hydroxide. So typically these guys will become sort of basic solution. You don't have to worry about the name of this guy here. But again, it basically can do, amines can basically act as bases, just like ammonia can, accepting that H plus from something, for example, like water. An ammonia salt is basically formed when we do such a reaction. That's the guy I crossed out the name of. It's basically an ionic compound, kind of similar to when we do an acid plus a base. We get water and a salt. Here we get an amine salt, which is basically because the base is starting out as an amine, which means we end up with basically a salt form of an amine. And remember, a salt form is really just a fancy word for an ionic compound. So same thing here. We take an amine with an acid like hydrochloric acid, it's going to donate its H plus over. It gains a plus, and the Cl minus comes in there to kind of balance out the charge. Same thing here, H plus going to come over. We gain an H and a plus, and this is again basically salts over here. You don't have to worry about the names of these guys, but that's basically again our amine working as a basically working as a base. Any questions on that there? Obviously, we don't get water in this case, but we do get the salt that's basically formed. Now, amines are usually converted to their ammonium salts before being used as some type of drug. Ammonium salts are solids at room temperature, odorless and soluble in water and body fluids. Here's some examples of that, some ingredients in medication. Again, here we see our amine salts happening in each of these cases here. Benadryl, Sudafed, decongestant. Also in obviously some other drugs like narcotics, cocaine. We also see here again our amine salt sort of happening, or really our amine here, which is right there. And through this process here can be converted into those through a base reaction here, again, really sort of an acid and base reaction happening with our kind of ammonium salts here, forming obviously cocaine in this case. Alkaloids are amines that are in plants, and they can also be found basically as a stimulant in things like nicotine. Again, you can see basically our amine functional groups here happening in these sort of compounds. Caffeine as well. We could see caffeine also, again, an amine, and also referred to as an alkaloid. And again, there's our sort of amine groups sort of happening on that compound. morphine and codeine as well. Again, you can see the amine groups happening here. So why don't we take a look at this here? Let's draw the condensed structural formula, or the line formula if it's cyclic for each of these guys: methylpropylamine and 2-chloroaniline. So take a second here and see what you come up with. Okay, let's take a look. We're going to work our way backwards like normal here. So we see amine. So we do know the functional group really is this. But really, it does resolve around the nitrogen. So that's really a good place to start, is as odd as it may sound, just with a nitrogen. So we see propyl, which is a 3-carbon group, and we see methyl attached to it. So since you're drawing it, you could do it either way. I'm going to put my methyl group to the right, and I'm going to put my 3-carbon propyl group to the left. I also know that what's left here is a hydrogen. And there we go. We now have our methylpropylamine. In this case, we can see this is actually a secondary amine, as it has 2 carbons attached. Question on that one there. Now, rolling this way, this is aniline. So remember, aniline basically is that traditional name, if you will, or historical name of basically a benzene ring that's got some amine group on it. So that's a pretty good place to start. Now I have 2-chloral. Because it's a number, that tells me it is a carbon that we're talking about here that it's attached to. If it wasn't a carbon and attached to the nitrogen, this would say N-chloral, right? So because it doesn't say N, we do see a number. Number means carbon. That is where it's attached. What we do know is this would then be carbon number 1, because that's basically where our mean functional group is located. And you could go left or right. Since you are drawing it, I will go right, and that would be carbon number 2. And then we're going to lay up a chlorine there. Question on that one. If it was N-chloroaniline, you would kind of do a similar thing here, except that attached to the nitrogen should be the chlorine, and then we would have a hydrogen. So that would be that guy. Again, N because the chlorine's attached to it. In this case, number means it's attached to a carbon. That is right there. Question on the difference between the two. Question on amines. So for amines, obviously you do need to know the functional group. You do need to know some of the solubility type functions of it. You need to know how to name it using the common name. Obviously draw them, based off of the common name. And that's pretty much what you need to know on that. And that they obviously react as a base. So like a Bronsted-Lowry base. Any questions on amines? All right, the last group is amides, and this is the final functional group here of an organic chemistry that we're going to talk about, and the final one that has nitrogen in it. It also has a nitrogen. It is similar to a carboxylic acid, except that it actually has an amine group attached to it. So it has that carbonyl group, and it has the amine group on there, and that's what we see right there. That's our amide bond. And as you could probably imagine, it is made from basically a carboxylic acid and an amine coming together to kind of make that sort of group. So amides are derivatives of carboxylic acid, again, because it's kind of where they come from. We do replace the OH group in a carboxylic acid with an amine group. And again, to show you sort of how it comes together to make an amide, We take a carboxylic acid. Again, that is our carboxylic acid right here. And we take something like ammonia. Are a primary or secondary amine. We'll also do this function. And basically what's going to happen here is we're essentially going to take out water in this reaction. So essentially, when these guys come together, out goes water. OH from the carboxylic acid, H from the amine or the ammonia. Obviously, that is where our water comes from. And then essentially, we just squish both sides together. So you can see CH3, CH3, CH2, CH2, carbon oxygen double bond, carbon oxygen double bond. Skip the water part. NH, NH, and H. So we just kind of squeeze it together. And this right here making our amide bond really, our carbon oxygen double bond and our NH3. Again, this is why it's really sort of similar to carboxylic acid because it kind of comes from a carboxylic acid. Same thing here, this propanoic acid along with a primary amine, methylamine, again, going to take out the water and gonna squish both of these guys together. We got our CH3, CH3, CH2, CH2, CO double bond, our NH, and our CH3 happening over here. So the way that you form an amide is what is referred to as a amidation reaction, which is a fancy way of saying basically take carboxylic acid and amine and squeeze everybody together, take out water. Any questions on that there? We can look at this. Here we go. If we want to predict what's going to happen, we're going to do the same type of thing. We're going to take out water and basically squeeze everybody together. So to help you do this, you might want to rearrange. This is our carboxylic acid. This is a primary amine. And if we sort of back up, and I'll even draw out maybe this guy, our amine here. We're going to take out water. So there goes water. And then basically everything stays the same. So in this case, we have a big ring structure. We also have attached to it a carbon oxygen double bond. Now remember, we took out the water, so we're going to pick up right here, which is really our amide connection. And we end up with this guy right here. Any questions on how that comes together? Okay. And that's what we see here. Again, some heat involved in this case. So carboxylic acid. An amine, primary or secondary, gets you an amide. And again, this right here is the functional group for the amide in that particular case. All right. So in terms of the amide, this is how you go about naming it. In both common IUPAC name, the amides are named by dropping the oic acid and putting the amide sort of suffix. Again, here we have the groups attached to the nitrogen. So we have the NN. Just for purpose sake here, this is the nitrogen that has a methyl and a methyl group. That is what the NN dimethyl means. And this is basically a 4-carbon group, which is based off of butane. Drop the E if you like and put amide, butane amide. The good news is you are not responsible for naming. So not responsible for naming amides. But in case you'd like to know, that's again basically how you do it. So you don't have to worry about naming amides. You do need to know the functional group, but you're not responsible to actually name it. Obviously, you need to know what they look like, but no actual naming you'll be responsible for. So it's up here in case you're curious and want to kind of know how to name it. We'll just kind of throw through it. But again, not necessarily responsible for it. Urea is the end product of protein metabolism. It's removed from the blood by the kidneys, excreted as urine. And you can see here it does have the amide group attached, or carbon oxygen double bond with the NH2. Again, this being its functional group here. Other things, barbiturates as well. We do see our amide group going that way, or the other way, really. And there's another one that's there. Aspirin as well, which is our aspirin substitutes, also sort of has that amide group happening. And again, here we see it down here. Now, amides do undergo a reaction, or two types of reactions that you do need to sort of be aware of. And they do undergo hydrolysis reactions. One is an acid hydrolysis, and one is a base hydrolysis. And kind of like what we talked about with hydrolysis reactions before, in the acid hydrolysis, you actually get back the carboxylic acid, and you do get an ammonium salt. So that is the case as we look, excuse me, down here. Here we have our amide, and we have our water. So if you think about the water here, it's going to kind of come in and break apart right there. That is going to get us back the completed carboxylic acid, which basically takes the HO out, leaving an H, and we do end up with 1H, 2H, and a C. So if we kind of keep track of everything, let me draw it a little bit bigger so it's easier maybe to see here. And acid hydrolysis with our HCl involved as well. So basically, we're going to break it right there, and we will then make the carboxylic acid back. And when you do that, you get the OH. And the OH you can think of as coming from here. So that kind of goes there. That leaves you, if you keep track, this part, which is basically a nitrogen and two hydrogens. Also, another hydrogen could come in and another hydrogen from there. And that basically makes NH4 plus. And there's also a Cl, which is Cl minus. It makes basically ammonium chloride, which is NH4Cl, basically, is what happens if you kind of keep track of everything that's going on there. If you do the base hydrolysis with heat, you produce a salt of the carboxylic acid, and you get the amine or ammonia back in that particular reaction. So let's take a look at that one here. I think there's a bigger picture here, maybe. Actually, let's take a look here. So if we do our sodium hydroxide, same idea. We're going to break it right there. And in this particular case, we will actually get the amine back. So we'll take the hydrogen out here, and we get the amine, which is right here. So again, CH3, CH3, nitrogen, hydrogen, nitrogen, and hydrogen, and the one hydrogen from the base. Remember, we kind of talked about, you could think of sodium hydroxide in this case as like H plus and ONA minus. And what happens is what's left is this guy will then go into here, and that's what we get at the end. So everything here is exactly the same as what it is up here. And then that's our ONA that comes into here. The oxygen actually connects. So in the base, what you get at the end is not the carboxylic acid, but you get this guy that's left over when you do the base hydrolysis. And that's different than when you do the acid hydrolysis, and we're talking about the carboxylic acid part, you get the full carboxylic acid back. So base, you get not the carboxylic acid, everything but the hydrogen. And the acid hydrolysis, you get the full carboxylic acid back. So that's the difference between the acid and the base. The acid protonates it, has the hydrogen on it. The base does not have it. So you can kind of think of it like base is OH minus. So I get like the minus part back without the hydrogen, and the acid is H plus. So it protonates it and comes back on. And that's the difference between those two. So acid hydrolysis, carboxylic acid comes back completely, and base hydrolysis, everything but the hydrogen comes back, and you do get the amine. Any questions on that there? So in terms of amides, what you need to know, again, is you need to know the functional group for an amide. You do need to know, how it's sort of made, which is made of basically a carboxylic acid plus an amine, primary or secondary. You need to know the acid base hydrolysis reactions, and you do not need to know no naming or drawing of amides from names or anything like that. So you won't be asked to name an amide, and you won't be asked to draw an amide from a name. The only amide that you may draw may be as part of a reaction, either the acid hydrolysis or base hydrolysis, but you won't be really asked to draw it or name it. So basically, very simple on amides, functional group, and how they're sort of made. Any questions on that? Okay, that does wrap up organic chemistry there, and officially chapter 14, and also wraps up discussion here. So as